take one breath. Notice that there is only one of you taking it. One body in this room, one nervous system listening, one version of this moment that you are the inside of. It feels, when you check, like the most ordinary fact in the world. In March of 1957, a 26-year-old graduate student at Princeton named Hugh Everett III submitted a doctoral thesis arguing that this is not what the equations of physics actually say. The equation he was looking at was the central equation of quantum mechanics, the Schrödinger equation, the piece of math that describes how the state of a physical system changes through time. The math is not controversial. Every physics graduate student on the planet learns it. Every laser and transistor and MRI machine in the world runs on it. The equation works. The argument is only about what the equation means. Everett's thesis made one move that nobody else had been willing to make. He took the equation literally. He insisted that the wave function, the object the equation describes, applies to everything, not just to electrons, not just to photons, to the measuring device, to the laboratory, to the observer, to the planet, to you. He gave that object a name. He called it the universal wave function. That phrase is the thread we will be following tonight. If the universal wave function is what reality actually is, then a great deal of what you take for granted about being alive becomes harder to defend. Because the equation has one specific property, and Everett refused to ignore it. The equation does not allow the wave function to collapse. Not ever. Not even when you look at it. Every time a quantum event has more than one possible outcome, the equation says all of the outcomes go on existing at once. They do not interfere with each other anymore. They do not communicate. But they all keep going forward. And inside each of them, there is a version of the observer who saw that outcome, and only that outcome. There are, by this account, versions of you who made every choice you did not make. The version who chose the other job. The version who said the thing you held back. The version who turned off this video before reaching this sentence. And the version who never opened it at all. That last one is real, in a precise technical sense we will get to. This is not the multiverse cosmology argues over. The other universes Everett was talking about are not far away. They are not on the other side of some cosmic horizon. They are right here in this room, on this exact branch of an object that has no edge. If the deep questions of physics keep you company at night, you are in the right place. Subscribe and settle in. The story ahead is the long arc of the actual paper Everett submitted in 1957. The story begins with John Wheeler, the advisor who cut the thesis to a quarter of its original length before letting Everett defend it. It runs through the disastrous spring of 1959, when Everett traveled to Copenhagen to meet Niels Bohr in person, and Bohr's group dismissed him so thoroughly that Everett described the visit afterward as hell. It picks up again decades later with physicists like Wojciech Zurek and Sean Carroll, who explain what it actually means to say the universe is branching. And it ends, if you stay with it that long, at the thought experiment that is supposed to prove the whole framework is correct if you have the nerve to perform it on yourself. When we come back, near the end, to the universal wave function, you will understand why a careful minority of working physicists believe this story is not science fiction at all. You will also understand which version of you is the one listening now. What quantum mechanics says in the version you would find in any physics textbook on the planet took shape between 1925 and 1927, mostly in two cities. Göttingen in northern Germany, where a small group of theoretical physicists led by Werner Heisenberg, Max Born, and Pascual Jordan worked out a formulation based on matrices. And Copenhagen, where Niels Bohr ran the Institute for Theoretical Physics on Blegdamsvej, and where Bohr's own interpretive framework would become the standard reading of the new theory for the next century. The physical idea that made Schrödinger's wave equation possible had been proposed 2 years earlier by a French aristocrat-turned-physicist named Louis de Broglie. De Broglie's 1924 doctoral thesis at the Sorbonne argued that all matter, not just light, exhibits wave-like behavior. The thesis was so unorthodox that de Broglie's committee referred it to Einstein for evaluation. Einstein wrote back, saying the work was important and should be accepted. De Broglie was awarded his doctorate. 3 years later, in 1927, the Bell Labs physicists Clinton Davison and Lester Germer confirmed the matter-wave hypothesis experimentally, demonstrating that electrons scatter from crystal surfaces with the diffraction pattern of waves. De Broglie won the Nobel Prize for the thesis in 1929. The equation everyone now learns first, the Schrödinger equation, came from neither of those cities. Erwin Schrödinger was a 38-year-old Austrian physicist working at the University of Zurich. He wrote his first wave mechanics paper during a Christmas holiday in the Swiss alpine village of Arosa at the end of 1925, in the company of a woman who was not his wife and whose identity has never been confirmed. The mathematics has been in continuous use for 100 years. The companion has remained anonymous for almost as long. What Schrödinger had written was an equation for an object he called the wave function. The wave function, written with the Greek letter psi, is not a physical wave in the way an ocean wave is a physical disturbance of water. It is a mathematical function defined over the possible states of a system. For a single electron, it assigns a complex number to every point in space, encoding both the probability of finding the electron at that point and the phase of its quantum behavior. The Schrödinger equation tells you how the wave function changes through time, smoothly, deterministically, with no surprises. Given a wave function now, the equation gives you the wave function in the next moment, and the moment after that, indefinitely. Heisenberg had arrived at the same mathematics from a different direction 6 months earlier. In June of 1925, suffering from hay fever, the 23-year-old Heisenberg had retreated to the small German island of Helgoland in the North Sea, where there was almost no pollen and no distractions. In a single late-night session there, he worked out the mathematical formalism that would become known as matrix mechanics. He wrote in his later memoir of finishing the calculation just before dawn, climbing to the top of a cliff on the island and watching the sun rise. Back in Göttingen, Born and Pascual Jordan recognized that Heisenberg's notation could be written cleanly in terms of matrix algebra. Within a few months, Heisenberg, Born, and Jordan had published the 3-author paper that formalized matrix mechanics, which Schrödinger would later show is mathematically equivalent to his wave mechanics. The two approaches, developed independently within 6 months of each other on opposite sides of Europe, describe the same physics in different mathematical languages. 3 months after Schrödinger's first paper, in the summer of 1926, Max Born at Göttingen proposed what the wave function meant physically. He suggested it was a tool for calculating probabilities. The squared amplitude of the wave function at a point gives you the probability of finding the particle at that point when you measure, not a tendency, not a likelihood that approximates some hidden classical reality. The probability itself. The probability is what the wave function is. Einstein read Born's proposal and refused to accept it. He spent the next 30 years arguing against the probabilistic reading of quantum mechanics in increasingly elaborate thought experiments, in famous letters to Bohr, in the line for which he is now most widely quoted. God does not play dice with the universe. Bohr won the Nobel Prize for the probability interpretation in 1954. Einstein died the next year, still insisting the interpretation was incomplete. Heisenberg, in 1927, added a constraint on top of the probabilistic picture, the uncertainty principle. The position and the momentum of a quantum particle cannot both be sharply defined at the same time. The more precisely you specify one, the less precisely the other can be specified. This is not a statement about measurement. It is a statement about what the wave function is allowed to be. There is no underlying reality where the electron has a definite position and a definite momentum, with our instrument simply too clumsy to read both at once. The electron does not have those properties simultaneously. The wave function does not contain that information because no wave function can. Wolfgang Pauli, in 1925, had added one more constraint to the framework: the exclusion principle. No two electrons can occupy the same quantum state. This single rule, applied to atomic physics, explains why matter is solid, why atoms have shells, why the periodic table of the elements has the structure it does. Pauli, born in Vienna and trained in Munich, was the youngest of the founding theorists. He had a reputation for ferocious mathematical rigor and a willingness to call anyone, including Einstein, wrong to their face. He won the Nobel Prize for the exclusion principle in 1945. He spent the rest of his career quietly at the Federal Institute of Technology in Zurich, where he had succeeded Einstein. By the autumn of 1927, the structure was in place. Schrödinger's wave equation, Born's probability rule, Heisenberg's uncertainty principle. Together, they made predictions that matched every experiment anyone could devise. They also raised a question nobody had a clean answer to. The question came from a simple thought. The wave function tells you the probability of every possible outcome of a measurement. When you actually make the measurement, you get one outcome. So what happened to the others? The answer that became standard was the work of Niels Bohr and the physicists who circulated through his institute in Copenhagen. It is now called the Copenhagen interpretation, although Bohr himself never used that term in print, and there is some dispute among historians about how unified the original Copenhagen view actually was. The answer, simplified to its essentials, runs like this. The wave function evolves smoothly under the Schrödinger equation as long as nobody looks at it. The moment a measurement happens, the wave function collapses instantaneously to one of the possible outcomes. The probability of any given outcome is given by Born's rule. Once collapsed, the wave function continues to evolve smoothly from that new starting point until the next measurement. This is, when you look at it directly, a strange answer. There are two different rules for how the wave function changes. One rule applies between measurements. A different rule applies during measurement. There is no equation for the collapse. There is no specification of what counts as a measurement, or how big the measuring device has to be, or whether a conscious observer is required. The Copenhagen interpretation simply asserts that this is how quantum mechanics works, and proceeds to make extraordinarily accurate predictions on that basis. Bohr's framing of the interpretation made one further claim, which he called the complementarity principle. Particles and waves, position and momentum, energy and time. These are not properties an object has independently of measurement. They are, in Bohr's view, complementary aspects revealed by different experimental setups. The principle was first articulated in a long lecture Bohr gave in Como, Italy, in September of 1927, and he refined it for the rest of his life. Complementarity is the deepest philosophical claim the Copenhagen interpretation makes. It is also the part Everett's framework would, 30 years later, refuse to accept. In Everett's reading, the wave function is a single object describing a single physical reality. Complementary descriptions are not necessary because there is no measurement that selects one aspect over another. There is only the wave function doing what the equation says it does. In October of 1927, 29 of the leading physicists of the era gathered in Brussels for the 5th Solvay conference on the theme of electrons and photons. The photograph from that conference is one of the most reproduced images in the history of science. 17 of the 29 in the picture would eventually win the Nobel Prize. The conference was where the Copenhagen consensus emerged in something like its final form, and where the long argument between Bohr and Einstein began. The argument lasted 30 years and never resolved. The form the argument took was a series of thought experiments. Einstein would propose a scenario in which the uncertainty principle appeared to be violated. Bohr would spend a sleepless night working through the scenario and find the flaw. By morning, Bohr would have a reply. Einstein would acknowledge the reply and propose another scenario, more elaborate. The most famous exchange came at the 1930 Solvay conference, with Einstein's clock-in-a-box experiment, in which an emitted photon could, in principle, be measured with arbitrary precision in both energy and time of emission. Bohr's response, delivered the next morning, used Einstein's own theory of general relativity to refute it. The gravitational redshift introduced by the weight of the photon altered the clock's rate. Einstein, the man who had discovered general relativity, had been undone by general relativity. The room watched him concede. Einstein never stopped objecting. In 1935, with Boris Podolsky and Nathan Rosen, he published a paper arguing that quantum mechanics had to be incomplete because the Copenhagen reading implied what Einstein called spooky action at a distance. That paper is now read as the founding document of quantum entanglement research, and the spookiness it describes has been confirmed repeatedly in laboratories. Einstein lost that argument too. The way he lost it would not be experimentally settled for another 50 years, but the verdict, when it came in, went against him. Also, in 1935, Schrödinger himself published the paper that everyone now half remembers, the cat paper. Schrödinger's intention, when he wrote it, was almost the opposite of how the paper has come to be quoted. He was not endorsing a picture in which a cat sealed in a box could be simultaneously alive and dead. He was pointing out, with the dry irony of a man who had grown impatient with his colleagues, that the Copenhagen interpretation, taken literally, would force you to conclude that a cat sealed in a box could be simultaneously alive and dead. He intended the example to be obvious enough that any reasonable physicist would back away from the interpretation that produced it. He was wrong about what his colleagues would do. They simply accepted the cat. What Schrödinger's paper actually said, in the long version most readers do not encounter, is more pointed. He wrote that the standard interpretation produced what he called quite ridiculous cases. He gave the cat as an example of how absurd things become if you take the formalism literally without the collapse postulate. The irony, which Schrödinger lived to see, is that his own intuition, that something more had to be added or removed to make the formalism describe a sensible world, would later be vindicated, but not in the direction he expected. Everett's solution, when it came, would not add anything to the formalism. It would remove the collapse postulate that Schrödinger had been pointing at. The cat would remain in superposition. The room would simply be redescribed as also being in superposition, with one branch containing a dead cat and one branch containing a live cat, and observers on each branch unable to access the other. What the next two generations of physicists were trained to do, with the Copenhagen consensus as their starting framework, was to stop asking the question. The pragmatic tradition has been summarized for decades by a phrase the physicist David Mermin used in a Physics Today column in 1989: "Shut up and calculate." Mermin was describing, not endorsing, the dominant teaching style. The phrase has often been misattributed to Richard Feynman, who said something similar but never that. The point of the phrase was that quantum mechanics gives you a procedure for predicting outcomes. The procedure works. The procedure has never failed an experimental test. Whether the wave function is a real physical object, or merely a calculation tool, or something stranger that nobody has yet articulated, is a question that has no observational consequence. So most working physicists, then and now, do not spend time on it. The pragmatic stance is defensible because the procedure really does work. Every laser in every supermarket scanner runs on the predictions of the Schrödinger equation. Every transistor in every computer chip uses the quantum mechanical tunneling probabilities calculated from wave functions. The atomic clocks at the heart of the global positioning system, the ones that allow your phone to pinpoint its location on Earth to within a few meters, run on quantum transitions whose frequencies are specified by quantum mechanics to many decimal places. Magnetic resonance imaging works because protons in your tissue have quantum spin states that align with applied magnetic fields in ways the equations describe exactly. Light-emitting diodes work for the same reason. The screens you read on, the fiber optic lines carrying these words, the integrated circuits in the device that played you this audio. All of it runs on a 100-year-old equation that nobody can fully agree on what it means. I want to draw one distinction here before we go any further, because the word multiverse is going to come up repeatedly in what follows, and the version of the multiverse we are talking about is not the version cosmologists usually argue over. The cosmological multiverse, the version associated with eternal inflation and the bubble cosmologies that Stephen Hawking spent the last years of his life trying to constrain, is a multiverse of other regions of space, other universes far away, separated from ours by an inflationary distance no signal can cross. The quantum multiverse, the one Everett's interpretation of quantum mechanics implies, is something different. The other universes Everett was talking about are not separated from us by distance. They are separated from us by a coordinate in an abstract mathematical space called Hilbert space, the same space the wave function lives in. They are not far away. They are right here. The version of Sean Carroll that already knows what you are about to think is not several billion light years over there. He is on a different branch of the same wave function, in the same room. That distinction matters because the loose thread we are about to pull is not the cosmological one. It is the strictly quantum one. And the thread is this. The Copenhagen interpretation, taken seriously, has two processes glued together with no joint mechanism. Between measurements, the wave function evolves under the Schrödinger equation. That evolution is deterministic, smooth, time-reversible, and uses no probabilities. During measurement, the wave function collapses. That collapse is instantaneous, random, time irreversible, and is governed by Born's rule. Nothing in the formalism of quantum mechanics tells you when one process becomes the other. There is no equation describing the collapse. There is no specified timescale for the collapse. There is no list of physical interactions that count as a measurement and physical interactions that do not. Bohr's own answer was to draw a line between the quantum world and the classical world, with measurement happening at the line, but he never wrote down where the line was. He could not. Nobody has. The classical world, as best modern physics can tell, is made of quantum particles obeying quantum equations. There is no line. There is no separate classical regime. There is only the quantum regime, with parts of it that happen to look classical when you are not looking too closely. Anyone who looked at this directly saw a problem. Schrödinger saw it. Einstein saw it. The young physicists trained on the Copenhagen interpretation in the 1930s and 40s saw it. Most of them, encouraged by Bohr's authority and the practical success of the formalism, decided to live with it. The problem is what philosophers of physics now call the measurement problem, and what Everett, in the summer of 1955, with Arger Peterson sitting across from him at a Princeton common room and a bottle of sherry between them, decided was no longer worth pretending was not there. Arger Peterson was 34 years old that autumn, a Danish physicist who had grown up inside Niels Bohr's institute in Copenhagen and was now spending a year at Princeton as a visiting scholar. He was, by every account, devoted to Bohr personally and to the Copenhagen interpretation philosophically. Peterson had spent more time in close conversation with Bohr than almost anyone alive. He had come to Princeton in part to evangelize, in the gentle way Danish theoretical physicists evangelized, for the framework his mentor had built over the previous 30 years. He found himself, in the autumn of 1955, in a graduate common room with two young American physics students who were unwilling to back down. One was Charles Misner, who would later become a major figure in general relativity and a co-author of the standard graduate textbook on the subject. The other was Hugh Everett III, 24 years old at the time, a year and a half into his doctoral work, with John Wheeler as his advisor. There is a recollection of that night that survives because Misner returned to it again and again in interviews across the decades. There was a bottle of sherry. The conversation ran late. Peterson defended the standard reading of quantum mechanics, that the wave function collapses on measurement, that observers stand outside the quantum domain, that any attempt to push the formalism past the line Bohr had drawn would only produce nonsense. Everett did not accept any of it. He kept pushing the formalism back at Peterson. He kept asking what physical process actually collapsed the wave function. He kept asking when exactly the collapse was supposed to occur. He kept asking why the formalism contained no equation describing it. By the end of the evening, with the sherry mostly gone, Everett had said out loud the thought he had been circling for months. If the Schrödinger equation describes the wave function correctly, and if the wave function never actually collapses, then quantum mechanics works fine, provided you are willing to accept that every possible outcome of every measurement keeps existing. Hugh Everett III had been born in Washington, D.C. on November the 11th, 1930. His mother was a poet who had separated from his father early in his childhood. His father was a career army officer who eventually rose to the rank of lieutenant colonel and served in both world wars. The young Everett was unusually mathematical from an early age. As a high school student, he had written a letter to Albert Einstein, asking how Einstein reconciled human free will with the deterministic equations of physics. Einstein wrote back, "The letter is preserved in the family papers. Everett kept it for the rest of his life. The letter has been published in several biographical sources, including Peter Burns' biography." Einstein addressed the teenager by name and treated his questions seriously. He wrote that there is no such thing as an irresistible force meeting an immovable body, but that there appeared to be a very stubborn boy who had forced his way through difficulties he had himself created. The reply was teasing. It was also the reply of one mind to another. Everett kept the letter and read it again as an adult. The young man who became convinced, by the time of his Princeton thesis, that determinism does not require collapse, that the equations do not need a special rule for human choice, had been thinking about that question since he was a teenager. He had taken his undergraduate degree at the Catholic University of America. He had arrived at Princeton in 1953 on a National Science Foundation fellowship. Wheeler had taken him on as a doctoral student, in part because Wheeler, who was famously open to unorthodox ideas, recognized in Everett a sharp and somewhat combative young mind. By the autumn of 1955, Everett was 24 years old, 6 feet 2 inches tall, dark-haired, given to cigarettes and martinis, and increasingly certain that the philosophical foundations of quantum mechanics, as they had been taught to him, were broken. It is worth saying a brief word here about Wheeler, because Wheeler will be the figure who both protects Everett and, in the end, agrees to the cuts that buried Everett's work. John Archibald Wheeler had been one of Niels Bohr's American disciples in the 1930s. He had worked at the Copenhagen Institute personally. He had collaborated with Bohr on the theory of nuclear fission in 1939. He revered Bohr and Bohr's authority in a way that complicates everything Wheeler would do over the next 2 years. Wheeler was also, by temperament, a generator of speculative ideas. He would later coin the terms black hole, wormhole, and quantum foam. He was the bridge between the founding generation of quantum theorists and the generation that would eventually take Everett's work seriously. The bridge held in both directions. Wheeler could not have championed Everett the way he did without his closeness to Bohr. He also could not have abandoned the project the way he eventually did without that same closeness. Everett's actual technical move in the months after the Sherry conversation was to take the Schrödinger equation literally and see what happened. The Schrödinger equation describes how the wave function changes through time. It is a deterministic equation governed by what physicists call unitary evolution. It does not anywhere in its mathematical structure contain a mechanism for the wave function to collapse. Collapse was a postulate the Copenhagen interpretation added on top of the equation, not something the equation itself required. Everett's question was simple. What happens if you do not add that postulate? What happens if you just let the equation do what it does? What it does, when you push it past the line Bohr had drawn, is something the Copenhagen interpretation had been specifically built to avoid. If the wave function applies to everything, to the electron and to the laboratory, and to the physicist holding the clipboard, then the act of measurement is not a special process that interrupts quantum mechanics. It is just another physical interaction governed by the same equation as everything else. The measuring device becomes entangled with the system it is measuring. The physicist becomes entangled with the measuring device. The room becomes entangled with the physicist. The Earth becomes entangled with the room. Take a concrete example. An electron passes through a Stern-Gerlach magnet, the standard laboratory device for measuring quantum spin. The electron enters in a superposition of spin states, half up and half down. The magnet, governed by the same Schrödinger equation as the electron, becomes entangled with the electron, so that the joint state of magnet plus electron is half magnet pointing left, electron spin up, and half magnet pointing right, electron spin down. A physicist looks at the magnet. The physicist, governed by the same Schrödinger equation, becomes entangled with the magnet. The joint state of physicist plus magnet plus electron is now half. Physicist sees magnet pointing left, electron spin up, and half. Physicist sees magnet pointing right, electron spin down. In the Copenhagen interpretation, this is the moment the wave function collapses. One outcome is selected, the other vanishes. In Everett's formulation, nothing collapses. Both outcomes continue forward inside the wave function, each containing a copy of the physicist who saw that outcome and only that outcome. The wave function, which now describes the joint state of all of those things, does not collapse to one outcome. It contains all of them. Every outcome that the Born rule assigns a probability to is now a branch of the joint wave function. Each branch contains a version of the physicist who saw that outcome, and only that outcome. From inside any one branch, the other branches are no longer accessible. They do not interfere. They do not interact. They cannot be measured. But by the equation, they are all still there. The wave function has not lost them. It has only stopped letting them communicate. This was the picture Everett wrote down. He called it the relative state formulation. The state of any one system is always defined relative to the state of every other system it has interacted with. There is no single absolute state of the universe in the way classical physics had assumed. There is one wave function evolving smoothly under the Schrödinger equation, and inside that wave function, the experience of any individual observer is one branch among many, defined by the chain of correlations that observer's state has accumulated. In January of 1956, Everett handed Wheeler a draft of the thesis. The title at that point was Quantum Mechanics by the Method of the Universal Wave Function. Wheeler had Everett retitle it Wave Mechanics Without Probability 3 months later, when the draft was first circulated to Bohr's group in Copenhagen. Wheeler read it. Wheeler was, by all accounts, excited. He understood that what Everett had written was something the field had needed for 30 years. He also understood immediately that what Everett had written would be heard in Copenhagen as an attack on the entire framework Bohr had built. Wheeler decided to handle the diplomatic problem himself. In May of 1956, Wheeler traveled to Copenhagen. He carried with him a copy of Everett's draft. He spent several days at the Institute talking with Bohr and with the resident physicists, including Leon Rosenfeld and Arge Peterson, who had since returned home from his Princeton year. Wheeler tried to present Everett's ideas in the most generous possible light. He failed. Bohr rejected the framework completely. Rosenfeld, in a letter Wheeler later showed Everett, called the approach theological and not worth serious consideration. The visit produced no support, no opening, no diplomatic path forward. Wheeler returned to Princeton in June with what amounted to bad news. The Copenhagen group would not accept the thesis as written. Wheeler urged Everett to rewrite the document in softer language, to frame the work as a clarification of the Copenhagen interpretation, rather than an alternative to it, to cut anything that read like a direct challenge to Bohr. Everett, who had now been working on the thesis for 18 months, agreed in principle and resisted in practice. The correspondence between the two of them across 1956 and 1957 is full of Wheeler asking for further cuts and Everett pushing back. By the autumn of 1956, Everett had concluded that the path through academic physics was narrowing. He was 25 years old. He had recently married a young woman named Nancy Gore. He had lost his student draft deferment, or was about to lose it, and the alternative was conscription as an enlisted soldier in peacetime. In October, he attended a 4-day weapons orientation course at Sandia National Laboratories in Albuquerque, New Mexico, learning about the design and effects of nuclear weapons. He came back to Princeton interested in defense work. By the end of the year, he had accepted a position with the Weapons Systems Evaluation Group at the Pentagon. The WSEG was a small, secretive office that performed quantitative analysis on military problems for the Joint Chiefs of Staff. It paid well. It came with a security clearance. It came, crucially, with a draft deferment. Everett did not yet have a doctorate. He worked on the thesis from Washington in evenings and on weekends, communicating by mail with Wheeler in Princeton. Wheeler kept insisting on cuts. The original long version, the one Everett had written in 1955 and early 1956, was philosophically thorough and unambiguous about its disagreement with Copenhagen. The version Wheeler eventually allowed Everett to defend was approximately 1/4 of the length of the original. Most of the philosophical argument was excised. Most of the explicit comparisons with the Copenhagen interpretation were removed. The cut version was given a new, more neutral title, On the Foundations of Quantum Mechanics. On March 1st, 1957, Princeton accepted the cut thesis. Everett received his doctorate in physics. The defense was a formality. He had been working at the Pentagon for almost a year by that point and did not return to academic physics afterward. In July, the short paper appeared in Reviews of Modern Physics in Volume 29 on pages 454 through 462. It was published under the title Relative State Formulation of Quantum Mechanics. Wheeler published a short companion paper in the same issue, attempting to reframe Everett's work in language Bohr might find less threatening. The companion paper did not help. The journal sent reprints to physicists around the world. There was almost no response. A few physicists wrote in with technical objections. Most simply ignored it. The paper that should have been the foundational document of a new interpretation of quantum mechanics was, in the year of its publication, one of the most ignored papers in the field. Rosenfeld in Copenhagen read the published paper in September and was no kinder to it than he had been to the draft a year earlier. His objection was specific. In Rosenfeld's reading, Everett had failed to understand that the line between the quantum world and the classical world is not optional. It is, in the Copenhagen view, what makes physics work as a science. Erase the line, and you have an interpretation in which no measurement ever resolves anything, in which the observer is just another quantum system inside a wave function that never decides what is real. Rosenfeld considered this not a deeper reading of quantum mechanics, but a fundamental confusion about what physics is for. The letter, like many of Rosenfeld's letters, was sharp. It also became, over the next several decades, the standard institutional response to Everett's work. The framework would be politely ignored by working physicists for the next 13 years, and the few who responded would mostly respond in something like Rosenfeld's tone. For the next 2 years, Everett worked at the Pentagon, calculating the casualties of hypothetical nuclear exchanges. He helped design the analytical framework that the Joint Chiefs would use to evaluate the United States military's master plan for fighting a nuclear war. He wrote computer code for nuclear targeting systems. Most of his work from this period remains classified 70 years later. The man who had argued, in his unread thesis, that the universe never resolves to one outcome, was now spending his working life calculating, with rigor, the outcomes of a war that had not happened yet and would not happen in any branch he wanted to live in. In the spring of 1959, Wheeler made one more attempt to rescue Everett's standing in physics. He arranged for Everett to travel to Copenhagen with his wife, Nancy, and their 2-year-old daughter, Elizabeth, and to meet Bohr in person. Wheeler believed, against the evidence, that if Bohr could only hear the argument directly from Everett in conversation, the impasse might be broken. The visit lasted 6 weeks, from late March into early May. Charles Misner was also in Copenhagen at the time, working at the Institute on his own postdoctoral research. He was a witness to what happened. Bohr was 73 years old. He had won the Nobel Prize 37 years earlier. The interpretation that bore his city's name was the dominant reading of quantum mechanics on the planet, taught in every graduate program, used by every working physicist. Bohr was, by all accounts in his last years, gracious and patient with visiting scholars. With Everett, he was neither. The two of them, with Arge Peterson and Leon Rosenfeld and other members of Bohr's circle present, met several times over the course of the visit. The conversations did not go well. Everett's framework, the universal wave function, the branches that never collapse, the observer as a quantum system inside the formalism rather than a classical agent outside it, landed in Bohr's group as either a misunderstanding of quantum mechanics or as a category error. Peterson, who had started the whole conversation in the Princeton common room 4 years earlier, did not come to Everett's defense. Rosenfeld, in private correspondence that surfaced years after his death, called Everett undescribably stupid and said he could not understand the simplest things in quantum mechanics. There is no surviving record of Bohr's own words to Everett. There is, however, a description of Bohr's body language from Misner, who watched the meetings from the corner of the room. Bohr did not engage Everett's argument at the level of the equations. He treated the framework as a philosophical confusion and waved it aside. Whatever Everett said, Bohr was already not persuaded. After the second or third meeting, the senior physicists in the room stopped pretending to engage. Everett, by the end of the visit, was speaking mostly to junior researchers and graduate students at the Institute, who were polite, and to Charles Misner, who was sympathetic but uncertain. Everett did not record his own version of the meetings in writing at the time. He spoke about the visit years later to interviewers and to friends. He used 2 phrases. He said the meeting had been doomed from the beginning. He said the experience had been hell. Charles Misner, who had been a quiet witness to all of this, did revise his view over the following decades. Misner had been sympathetic to Everett's framework at the time, but uncertain. Working on general relativity and gravitational physics at the University of Maryland through the 1960s, 70s, and 80s, he kept returning to the question. He was interviewed by Peter Byrne, by the Nova producers, and by other historians of physics multiple times across the late 20th century. His testimony became one of the primary historical sources for what happened in 1955 and 1959. Misner described Bohr in those late interviews as having simply refused to engage with the equations Everett was pointing at. He described Everett as having been wounded by the rejection in a way that he had not fully understood at the time. He described Wheeler, his own thesis advisor as well as Everett's, as having been caught between competing loyalties that he could not finally reconcile. Misner lived to be 91. He died in 2023, having outlived Bohr by 61 years and Everett by 41. He returned to Washington in May. He never published another paper on quantum mechanics. He spent the rest of his working life on classified defense analysis. He continued, in private conversation with the people who knew him, to believe that his thesis was correct. He simply stopped trying to convince anyone of it. Whatever the rejection had cost him, he carried it for the next 23 years, mostly in private, in the form of cigarettes and martinis, and a marriage that grew increasingly distant. He would die in 1982 at 51 of a heart attack at home. By that point, the framework he had abandoned had begun, very slowly, to find defenders. By that point, he no longer particularly cared. The long manuscript, the one Wheeler had ordered cut, contained the philosophical machinery the short paper deliberately omitted. It worked through explicitly the question of what happens when an observer becomes entangled with a quantum system. It developed a careful theory of how relative states accumulate as observers chain together their measurements. It included an extended discussion of the role of memory and information in physical observation. It also, in passing, made the claim that has since become the most quoted line from Everett's work, that the formalism, taken seriously, requires the wave function to contain every possible observer state, with each observer state being equally part of the wave function and equally real. The phrase, the universal wave function, does not appear in the cut version of the thesis Princeton accepted in 1957. It does not appear in the short paper published that July in Reviews of Modern Physics. It only appears in the long version Everett had written before Wheeler ordered the cuts. That long version sat in Wheeler's filing cabinet for over a decade after Everett left academia. It was, in every practical sense, the actual thesis Everett had wanted to defend, suppressed by the diplomatic concerns of a generation of physicists who did not want to anger Niels Bohr. The long version would sit in Wheeler's filing cabinet for over a decade. It would not see print in the form Everett had wanted until well after he had left physics entirely. The phrase that is the recurring thread of this story is the title of the actual paper Everett wrote, and the actual paper that the establishment for almost 20 years would not let him publish. The question Everett's framework left on the table after he stopped publishing and disappeared into the Pentagon was the one Bohr's circle had specifically refused to engage with. If the wave function does not collapse, then the other outcomes do not vanish. They keep going. So what does it actually mean, physically, for them to keep going? In what sense are they real? In what space do they exist? What does it mean, in concrete mechanical terms, for a branch of the wave function to be a place where a version of the world keeps unfolding? It took 13 years after Everett walked out of Bohr's Institute for someone to begin building a serious mathematical answer to that question. The work that finally produced one was not done in Copenhagen. It was done at the University of North Carolina by a Texan physicist named Bryce DeWitt, who took up the project as a vindication, and then at Los Alamos National Laboratory by a young Polish physicist named Wojciech Zurek, who built the mechanism that would eventually make Everett's framework legible as physics rather than as philosophy. So the question became, how? The starting framework for asking the question had been laid out 3 decades earlier, in 1932, by the Hungarian-American mathematician John von Neumann. Von Neumann's textbook, Mathematical Foundations of Quantum Mechanics, was the first rigorous mathematical treatment of the theory, and it is still in print. The textbook formalized two distinct processes by which the wave function can change. Process 1 was the smooth unitary evolution described by the Schrödinger equation. Process 2 was the discontinuous, probabilistic collapse triggered by measurement. Von Neumann gave both processes precise mathematical expression. He also pointed out in passing that he could not specify what physical mechanism distinguished Process 2 from Process 1. The line between them was, in his framework, a postulate. He chose to leave it that way. The decoherence work, when it finally arrived, would be an attempt to derive Process 2 from Process 1 without postulates. Bryce Seligman DeWitt was a Californian physicist born in Dinuba in 1923, who had moved to the University of North Carolina at Chapel Hill in 1956 as the founding director of the Institute of Field Physics. He would remain there for 16 years before moving on to the University of Texas at Austin. He had been one of the founders of canonical quantum gravity in the 1950s. He had written to Everett in 1957, shortly after the Reviews of Modern Physics paper came out, with technical objections. His objection at the time was the obvious one. The real world, DeWitt wrote to Everett, does not branch. If it did, we would feel it branching. We would feel the splitting. We would have some sensory experience of being one of the many. We do not feel any such thing. The continuous experience of a single self in a single world is not a small piece of evidence. It is the largest piece of evidence we have. Everett's reply was a single sentence. I can't resist asking, do you feel the motion of the earth? DeWitt did not have a good answer at the time. He did, however, keep the letter. Over the next 13 years, he kept turning the question over. By 1970, DeWitt had become an Everettian. He published an article in Physics Today titled Quantum Mechanics and Reality, in which he defended Everett's framework, used the "Do you feel the motion of the Earth?" reply against the Copernicus skeptics, and gave the framework a new name. He called it the Many Worlds Interpretation. 3 years later, in 1973, DeWitt and one of his graduate students at North Carolina, Neil Graham, edited an anthology for Princeton University Press. The book gathered Everett's original short paper, Everett's full long manuscript that had been suppressed since the early thesis, Wheeler's defensive companion paper, DeWitt's own commentary, and a number of new technical papers extending the framework. The book was titled simply The Many Worlds Interpretation of Quantum Mechanics. The print run sold out. For the first time, the actual paper Everett had wanted to publish, the long version titled The Theory of the Universal Wave Function, was in circulation, 16 years after Everett had been forced to cut it. To follow what happens next, you need to know what kind of space the wave function actually lives in. Not three-dimensional space, not even four-dimensional space-time. The wave function lives in something called Hilbert space. Hilbert space is a mathematical object, not a physical one. It is the set of all possible states a quantum system can occupy. For the simplest possible quantum system, a single particle that can be in just two states, like an electron spin pointing up or down, Hilbert space is two-dimensional, and a state of the system is a vector in that two-dimensional space. For a particle in three-dimensional physical space, Hilbert space is already infinite-dimensional because the particle can be at any of infinitely many positions. For the universe as a whole, with every particle and every field and every degree of freedom, Hilbert space has a dimensionality so high that the word infinite is almost an understatement. The Schrödinger equation, the central equation Everett refused to add the collapse postulate to, is fundamentally an equation for how a vector rotates inside Hilbert space, smoothly, unitarily, without ever shrinking or splitting. The wave function is that vector. It rotates continuously through the abstract state space. Different regions of Hilbert space correspond to different physical situations. The branching Everett's framework describes is a branching of that vector's direction in the abstract state space into orthogonal regions that no longer overlap. The version of the physicist who saw spin up and the version who saw spin down are not separated in three-dimensional space. They are separated in Hilbert space by a structural feature that prevents the two versions from ever interacting again. Max Tegmark at MIT has put this distinction more sharply than anyone. The only difference, Tegmark writes, between the spatial multiverse, the doppelgangers 1,000 trillion meters away in an infinite universe, and the quantum multiverse Everett's framework implies, is where the other versions reside. In one, they live elsewhere, in good old three-dimensional space. In the other, they live on another branch of an infinite dimensional vector space that has no spatial location. The universal wave function is the only thing that exists. There is one wave function. It contains everything. Decoherence is the name physicists give to the physical mechanism that explains why we never observe macroscopic superpositions. It is, when you look at it clearly, the answer to DeWitt's 1957 objection. The reason you do not feel the branching is not that the branching does not happen. The reason you do not feel the branching is that decoherence makes the branches stop interacting with each other so quickly that no observer inside any branch can ever notice the others. The originating paper on decoherence is not from Zurich. It is from a German physicist named Heinz-Dieter Zeh, who published in 1970 a paper in the journal Foundations of Physics titled On the Interpretation of Measurement in Quantum Theory. Zeh's paper was almost as ignored at first as Everett's had been a decade earlier. Zeh was at the University of Heidelberg. His insight was this: quantum systems are not isolated. Real laboratory systems, real observers, real measuring devices are constantly being bombarded by photons and air molecules and thermal radiation. The environment is everywhere. The environment is what every quantum system is interacting with all the time. The system cannot avoid being entangled with the environment. Zeh's calculation showed what that constant entanglement does to a superposition. A superposition of two macroscopic states of a measuring device, pointer left and pointer right say, becomes entangled almost instantaneously with whatever else is in the room. Photons scattering off the pointer carry information about its position. Air molecules bumping into the pointer carry information about its position. Within a femtosecond, the joint state of the pointer plus the environment is no longer a clean superposition of pointer left and pointer right. It is a much more complicated thing in which the two branches have become correlated with billions of environmental degrees of freedom that no observer can ever practically track. To put a number on it, a dust grain about 1 micrometer across, sitting in normal room air, decoheres in something like 10 to the negative 31 seconds. That is 1/1,000,000 trillion seconds. A typical macroscopic object, a coffee cup, a cat, a clipboard, decoheres essentially the instant it interacts with any photon. If you were to compare the decoherence time to the time it takes light to cross an atomic nucleus, the decoherence is faster than that by many orders of magnitude. This is why nobody has ever, in the history of laboratory science, observed a superposition of a macroscopic pointer. The branches do not interfere because they cannot. The information about which branch is which is spread instantly and irreversibly across an environment too large to be reconstructed. The decoherence is not a metaphor, it is a quantitative mechanism with calculable timescales. Erich Hughes and Heinz-Dieter Zeh published the foundational quantitative calculations in 1985. Subsequent work by Wojciech Zurek, by Murray Gell-Mann and James Hartler, and by many others, has filled in the details. The picture is, by the standards of theoretical physics, well established. What decoherence does not do by itself is tell you what happened to the other branch. Decoherence explains why you only see one. It does not explain whether the other one is still there. That part is a matter of interpretation. If you adopt the Copenhagen view, you can say that decoherence is just a mechanism that makes the collapse postulate cleaner. The wave function effectively collapses because it cannot interfere with itself anymore. If you adopt the Everettian view, you say that decoherence is the mechanism by which a single wave function develops effectively non-interacting branches, each containing a copy of the observer. The mathematics is the same in both interpretations. The choice of which to believe is, in the strict empirical sense, a choice you cannot test with any conceivable experiment. The universal wave function never collapses, it branches, and every branch keeps going. Wojciech Zurek represents the next layer of the mechanism. Zurek was born in 1951 in Bielsko-Biała in southern Poland. He took a master's at the AGH University in Krakow in 1974 and a doctorate at the University of Texas at Austin in 1979. He spent 2 years at Caltech as a Tolman Fellow, then arrived at Los Alamos National Laboratory in New Mexico in 1984 as an Oppenheimer Fellow. He would spend the rest of his career there, eventually becoming a laboratory fellow in the theory division in 1996. Zurek's central contribution to the foundations of quantum mechanics began with 2 papers in the early 1980s. The first, published in Physical Review D in 1981 under the title Pointer Basis of Quantum Apparatus, Into What Mixture Does the Wave Packet Collapse?, introduced the concept of einselection. The second, in 1982, expanded the framework. Einselection is short for environment-induced superselection. The idea is that the environment, by constantly monitoring a quantum system, does not just decohere it, it also selects a preferred basis, a particular set of states that are stable under the monitoring. Other states would, in principle, also be allowed by the formalism, but they would not survive the environment's interaction. They would decohere into other combinations almost instantly. The stable states are called pointer states. They are the states the environment lets exist long enough to be observed. This is, when you understand what it is doing, what makes the classical world look classical. The reason your coffee cup is in a definite position on the table and not in a quantum superposition of being on the table and being on the floor is that position is one of the pointer states for a coffee cup interacting with the air and the light in your kitchen. Position is what the environment selects. Other quantum states of the coffee cup, quantum mixtures of definite position and definite momentum, would decohere into position states essentially instantly. The classical world is the world of the environment's pointer basis. Zurek extended this picture over the next several decades into what he calls quantum Darwinism. The metaphor is biological. The pointer states are the states that survive the environment's monitoring. The other states do not. The environment, by interacting with a system, copies information about the system's pointer state into many environmental degrees of freedom, into the photons scattering off the system, into the air molecules bouncing off it. Many independent observers can read out the same information from different parts of the environment and agree on what the system is doing. That agreement in Zurek's framework is what objectivity is. It is not built into the laws of physics from the beginning. It emerges dynamically from the environment's selection of which states get to persist. What Zurek's mechanism does, that earlier work had not done, is give a fully quantum mechanical account of why the classical world looks classical. The mechanism uses only the Schrödinger equation, only standard quantum mechanics, only the kind of entanglement Everett had described in 1957. There is no collapse postulate. There is no special role for observers. There is only the wave function and the environment interacting in the way the equations describe. For Everettians, this is the missing piece. The framework Everett had laid out in his thesis was philosophically coherent, but mechanically incomplete. He had said the wave function branches without collapsing, but he had not specified the physical mechanism by which a branch becomes effectively independent. Decoherence and einselection, developed without explicit reference to Everett through the 1970s and 80s, turned out to be exactly the mechanism his framework had been missing. The mechanism Zurek had described was extended through the 1980s and 90s by other physicists working at the boundary between quantum theory and the foundations of statistical mechanics. In 1983, Anthony Leggett and his former doctoral student Amir Caldera published a quantitative model of how dissipation works in quantum mechanical systems coupled to thermal environments. The work had been done largely at the University of Sussex, where Caldera had taken his doctorate under Leggett. Leggett was in the process of moving to the University of Illinois at Urbana-Champaign when the paper appeared. Their paper, which appeared in the Annals of Physics, gave specific calculations of how quickly decoherence would proceed for systems of different size and at different temperatures. The Caldera-Leggett model became the standard reference for any calculation of decoherence timescales. It established in numbers what Zay had argued qualitatively in 1970. The classical world is not a separate regime. It is the quantum world after decoherence has had time to do its work, and the time decoherence takes can be calculated. In 1990, Murray Gell-Mann at Caltech and James Hartlaw at the University of California at Santa Barbara published a framework they called the decoherent histories approach to quantum mechanics. Gell-Mann had won the Nobel Prize in 1969 for the discovery of quarks. Hartlaw had collaborated with Stephen Hawking on the no-boundary proposal for the origin of the universe. Their decoherent histories framework was an attempt to formalize what counts as a sequence of events in a quantum universe without depending on a special role for observers. A decoherent history is a sequence of quantum events whose probabilities, due to the action of the environment, behave in the way ordinary classical probabilities behave. The framework gave a precise mathematical sense to the intuition that the universe contains many possible histories, only some of which are consistent enough to be experienced. Many Everettians read decoherent histories as essentially equivalent to MWI in different language. Gell-Mann and Hartlaw, in their original papers, were more cautious. They positioned the framework as compatible with multiple interpretations, including a single world reading. What was still missing, even after the decoherence work, was an answer to the question Born had built into quantum mechanics in 1926. The Born rule. The squared amplitude of the wave function gives the probability of each outcome. In the Copenhagen interpretation, this is a postulate. In Everett's framework, where all outcomes occur, it is unclear what probability even means. If every outcome happens, in what sense is one outcome 99% likely and another 1% likely? The work on this problem moved, slowly, from American physicists like DeWitt and Zurich to a small group of philosophers and physicists at Oxford University. The Oxford program, as it is now called, emerged through the 1990s and 2000s. The central figures were David Deutsch at the Clarendon Laboratory, who had spent the previous 2 decades founding the field of quantum computation, Simon Saunders in the philosophy of physics, David Wallace, then Saunders's graduate student, who would publish in 2012 a book called The Emergent Multiverse, which became the most rigorous philosophical defense of MWI ever written, Hilary Greaves, who worked on the probability problem specifically. Deutsch had argued, going back to his 1985 paper on quantum computation, that quantum computers literally require the existence of the parallel branches Everett had described. To make the argument concrete, consider what a quantum computer running Peter Shor's algorithm does. In 1994, Shor, then at Bell Labs, published an algorithm that uses quantum interference to factor large numbers exponentially faster than any classical algorithm can. The algorithm exists. Small quantum computers have run it, factoring small numbers. Larger quantum computers, when they exist, will factor numbers that classical computers cannot factor in the age of the universe. The question Deutsch asked is where, physically, the computation is happening. A classical computer factoring a number does a discrete sequence of operations on bits, each operation taking place in a definite physical location at a definite time. A quantum computer factoring a number using Shor's algorithm does, in some sense, all the relevant operations at once, in superposition, with the interference at the end producing the answer. Deutsch's argument is that this superposition is not just mathematical bookkeeping, it is a description of the physical fact that the computation is taking place in many parallel branches of the wave function simultaneously, with the answer emerging from the interference between them. If MWE is wrong, Deutsch asks, then where is Shor's algorithm running? The decision-theoretic argument that Deutsch and then Wallace developed runs roughly this way. Imagine a rational agent inside an Everettian universe who is about to bet on the outcome of a quantum experiment. The agent knows that every outcome will occur in some branch, but the agent has to choose how to weight the branches when deciding how to bet. Deutsch and Wallace argued, with considerable mathematical machinery, that the only consistent weighting is to weight each branch by the squared amplitude of the wave function in that branch. The Born rule, in this argument, falls out as a theorem of rational decision theory, rather than as an extra postulate of quantum mechanics. The argument is controversial. Critics, including the philosopher David Albert and the physicist Adrian Kent at Cambridge, have argued that the decision-theoretic derivation is circular, that it smuggles in the Born rule under another name. The argument is, as of this recording, not fully resolved within the philosophy of physics community. The fairest summary is that the Oxford program has made the Born rule problem much sharper than it was 30 years ago, and has produced one defensible answer to it, but has not made the question go away. The popularizer who has done the most to bring all of this into wider conversation is Sean Carroll, an American theoretical physicist who spent most of his career at the California Institute of Technology before moving in 2022 to Johns Hopkins University, where he holds the Homewood Chair in Natural Philosophy. Carroll took his doctorate at Harvard in 1993 and has worked across cosmology, general relativity, and the foundations of quantum mechanics. In 2019, he published a book called Something Deeply Hidden, in which he argued, as forcefully as any working physicist has argued in the past 50 years, that the many worlds interpretation is not just defensible, but is actually the simplest possible reading of quantum mechanics. The argument Carroll makes most clearly is the parsimony argument. The Copenhagen interpretation has two processes glued together: the smooth unitary evolution between measurements and the instantaneous random collapse during measurement. The collapse is an extra postulate, not derivable from the equation. It has no mechanism, no specified timescale, no clear trigger. The many worlds interpretation, by contrast, has one process: smooth unitary evolution applied to everything all the time. The branches come for free out of the equations. The collapse postulate is simply dropped, because in the many worlds reading, there is no collapse. By Occam's razor, the simpler theory should be preferred. The simpler theory is the one with fewer postulates, not the one with fewer branches. Branches are not postulates. They are consequences. The collapse is a postulate. Drop the postulate, and the branches appear. The wave function predicts everything quantum mechanics predicts, with none of the extra collapse postulate. The branches are not an addition. They are what is left when the addition is removed. The question is not yet settled in the physics community. It may never be settled, in the sense of being decidable by experiment, because the predictions of MWI and Copenhagen are mathematically identical for every observable quantity. But the question of what working physicists actually believe has been measured. In 1997, Max Tegmark conducted an informal poll at a quantum mechanics workshop at the University of Maryland. Of the 48 participants, 27% picked the Copenhagen interpretation as their preferred framework. 17% picked many worlds. 8% picked the Bohmian pilot wave interpretation. The remainder were scattered across other views or had none. Tegmark, in his published report, framed this as a sign that Copenhagen's grip was loosening. In 2013, Anton Zeilinger and his collaborators, Maximilian Schlosshauer and Johannes Kofler, conducted a more formal poll, surveying participants at a conference on quantum foundations in Austria. 42% picked Copenhagen, 18% picked many worlds. 21% of respondents admitted to having switched interpretations multiple times in their careers. One participant wrote that he sometimes switched interpretations several times a day. In 2016, Sujeevan Sivasundaram and Christian Wittfeldt Nielsen polled 149 physicists across 8 universities. Their results gave Copenhagen 39% and many worlds 6%, with 36% expressing no preference at all. In 2025, in connection with the centenary of quantum mechanics, the journal Nature ran the largest formal survey ever conducted on the question, drawing more than 1,100 responses. 36% of respondents picked Copenhagen. Around 15% picked the branching interpretations, which the survey grouped together as many worlds and consistent histories. The remainder were spread across more recent epistemic and information-theoretic interpretations. The picture across 30 years of polling is consistent. Copenhagen has remained the most popular interpretation, never with a true majority, but always in the high 30s to low 40s. Many worlds has remained the strongest alternative, holding stable around 15 to 18%. It has not won. It has also not gone away. The popular claim, sometimes made by Carroll and Tegmark and others, that physicists secretly believe many worlds and just do not admit it, is not supported by the polls. The polls show a substantial minority who hold it openly, and a much larger pragmatic majority who have not made up their mind. there are serious physicists who do not buy it. Sabine Hossenfelder, in a widely circulated essay titled "The Trouble with Many Worlds," argued that the branching picture is not a literal description of reality, but a heuristic that obscures the underlying continuous evolution of the wave function. Adrian Kent at Cambridge has objected for 30 years that the Born rule cannot be derived from the formalism without smuggling probability back in. Other critics have raised the preferred basis problem, the branch counting problem, the question of personal identity across branches. The framework is not without intellectual difficulty. What it does have, after 7 decades of slow development, is a complete physical mechanism. Decoherence explains why you only see one branch. Ein's election explains which branch you see. Hilbert space provides the mathematical structure. The Oxford program offers a defense of the Born rule. The polls show that a substantial minority of working physicists accept this whole picture as physics rather than as philosophy. If the picture is correct, the implications are not abstract. They are not about distant galaxies. They are not about hypothetical aliens. They are about you, the specific you, the body in this room, the breath that is happening as you hear this, the version of you that did not turn off this audio, the version of you that did, the version of you somewhere in the wave function that has already died this evening on some branch from which the news will never reach the branch you are listening on. That last claim, in its full form, is what the next part of this story is going to take seriously. If the theory is correct, the implications are not small. They are not abstractions to be admired from a distance. They begin in this room. They begin with the version of you who turned off this audio before reaching this sentence. That version is the one I want to look at first, not as poetry, as a precise technical claim about what the wave function contains. Picture the moment a few hours ago or a few days ago when you first encountered this video. The thumbnail loaded on a screen. The title sat next to it. Some combination of habit and curiosity and timing brought your hand to the trackpad or the touchscreen or the remote. You pressed play. That moment, like every moment of human decision, was governed by the firing of billions of neurons in a brain. Every neuron fires when ion channels open, and those ion channels open according to electrochemical processes that are, at the relevant fine-grain, quantum mechanical. The thermal noise inside your nervous system is quantum noise. The exact timing of any individual neural firing depends on the quantum behavior of ions crossing membranes. The macroscopic decision whether your hand moved to press play was the integrated output of billions of such micro events. In standard, single-world quantum mechanics, all of that quantum noise averages out into a single classical outcome. You pressed play, or you didn't. Whichever happened, happened. The other possibility, if it ever existed, is gone. In Everett's framework, none of those micro-events resolved to a single outcome. Each one branched the wave function, the combinatorial structure of billions of micro-events, integrated through your decision process, produced an enormous number of branches. In some of them, the neural firings combined into the decision to press play. In others, they combined into scrolling past. In still others, they combined into closing the device entirely. All of those branches exist inside the wave function. Decoherence has long since rendered them unable to interact. From inside the branch where you press play, the branches where you did not press play are invisible. From inside those other branches, this video does not exist for you. This is the version of you the hook promised. The version who never opened this video at all. There is, by the equations Everett refused to add the collapse postulate to, a region of the wave function in which a person with your name and your face and your memories and your apartment never encountered this content. That region is not somewhere else in space. It is on a different branch of the same wave function, in something like the same room. The branch where you reach this sentence is one branch. The branch where you closed the tab 3 minutes ago is another. Both contain a person who, until the moment of branching, was indistinguishable from you. After the branching, only one of them is here. Only one of them, inside the experience the wave function gives them, is the one you are. The question that follows from the picture is one philosophers have been asking for centuries, in a form that did not require any physics. Which one is really you? The framework is, on this question, unequivocal. None of them is more real than any other. All of them, equally, are continuations of the person you were before the branching event. The version that pressed play and the version that did not press play are, in the structural language of MWI, equally weighted branches of the same wave function. There is no fact about which one is the real you. There is no preferred branch. This sounds on first hearing like a kind of disturbing relativism. It is, on closer inspection, not as strange as it sounds. The British philosopher Derek Parfit, in his 1984 book Reasons and Persons, argued at length that personal identity is not what most people think it is, even in a single-world universe. Parfit's thought experiments about gradual replacement of brain cells, about teleportation, about fission cases in which a person is duplicated, argued that the concept of the same person over time is much less determinate than ordinary intuition suggests. The most famous of those thought experiments is the teletransporter. Imagine a machine that scans your body at the atomic level, transmits the information to Mars, and reconstructs you there from local atoms. The original is then destroyed. Did you die, or did you travel to Mars? Parfit argued that this question, when you look at it carefully, has no determinate answer. Either you say the reconstructed person is you, in which case identity is preserved through complete material discontinuity, or you say the original died, in which case ordinary survival from one moment to the next, which also involves significant material change, is harder to defend than it looks. What matters in Parfit's framing is not a metaphysical fact about which entity is the same person. What matters is psychological continuity, the connections of memory, personality, and intention that link one moment to the next. In an Everettian universe, Parfit's argument generalizes naturally. Personal identity is a branching tree, not a line. Each branch contains psychological continuity with the branches before it. At any given moment, the person you are is one continuation among many. There is no privileged thread running through the tree. Parfit himself did not write about MWI. He was working in single-world philosophy. But his framework anticipates the question that MWI forces by other means. In Parfit's world, your identity is already a tree, in a smaller way, even before quantum branches enter the picture. The version of you who reads this sentence and the version of you who read it 5 minutes ago are connected by psychological continuity, by overlapping memory, by the persistence of personality and intention. They are not the same person in a metaphysically strict sense. They are the same person in the only sense the word usually means, which is that one is a continuation of the other. In an Everettian universe, the tree is wider. There are multiple continuations branching off from each moment. The framework does not invalidate identity. It just notices that identity, at any given moment, has more than one future. This is the point in the framework where many critics balk. The objection is intuitive. Surely I am one person in one branch, having one continuous experience. The branches I do not occupy are not me. The Everettian reply, given by Saunders and Wallace and others, is that this intuition is exactly the intuition any single branch would have. From inside the branch where you pressed play, the experience of being here is continuous and uniform. From inside the branch where you did not, the experience of not being here is equally continuous and uniform. Both of those experiences exist. The wave function does not choose between them. It contains them both. The wave function does not have a preferred branch. Every branch is equally part of it. There is no real you and less real yous. The implication for choice is what most viewers find hardest to sit with. If every quantum-influenced decision branches, and every branch contains a version of you who made the other choice, what does it mean to say that you chose anything? The version who chose differently is also you. The version who walked away from the argument walked away. The version who picked up the phone picked it up. None of them is more real than any other. What MWI does, paradoxically, is take away some of the metaphysical weight of regret. Every regret you have about a choice you did not make has, inside the framework, a branch in which you made the other choice. The branch is real. The version of you in it experienced the consequences. Whether the consequences were better or worse, in that branch, is a question with an answer, even if you cannot access it. This is not a comforting picture. It is, for most people, a stranger and more vertiginous picture than they expected. The point of MWI is not to soften the experience of being human. The point is to take the equations seriously. The vertigo is the cost of that seriousness. There is a question even MWI cannot easily answer, and it is the question that has driven most of the technical work since the 1990s. The question is, why do you experience the probabilities you experience? Quantum mechanics predicts, through the Bohr rule, that some outcomes are more likely than others. When you measure the spin of an electron in a particular superposition, you may get up with 99% probability and down with 1% probability. If you run the experiment 1,000 times, you will get something like 990 ups and 10 downs. The Bohr rule is one of the most precisely tested predictions in all of physics. In a collapse interpretation, this is straightforward. The wave function collapses randomly, weighted by the squared amplitude. The frequencies you observe match the probabilities the rule predicts. In Everett's framework, this is not so straightforward. Every outcome happens. There is a branch in which the electron came up down. There is a branch in which it came up. There is a branch in which it came up 990 times in a row. There is also a branch in which it came up down 990 times in a row, in defiance of every textbook prediction. From inside that branch, the textbook prediction is wrong. The version of you on the unlikely branch is just as real as the version of you on the likely branch. The unlikely branch is just as much a part of the wave function as the likely one. So what does 99% probability mean when both outcomes happen in some branch and the framework treats them equally? The Oxford programme's decision-theoretic answer is that a rational agent inside MWI should bet as if probabilities match the Bohr rule, because doing so is the only consistent betting strategy. The critics' answer is that this is circular. The fairest summary is that the question remains open, and the framework still has to answer it. There is a related problem in the framework that critics have raised since the 1960s, called the branch counting problem. The problem is roughly this. If every quantum event branches the wave function, then most branches contain runs of events that statistically would be impossible in a single world universe. There are vastly more branches in which improbable things happened than in which probable things happened, if you just count branches. The branches in which the unlikely outcome occurred outnumber the branches in which the likely outcome occurred, in some natural sense of counting. Why then do we live in branches where probabilities behave the way the Bohr rule predicts? The answer, the Oxford programme argues, is that branches are not all equal. They are weighted by amplitude. The weighting is the Bohr rule, derived from decision-theoretic considerations. The critics reply that this is exactly what needs to be derived independently, and that the derivations are circular. The fairest summary is that this part of the framework is still being worked on by both defenders and critics in the journals where philosophers of physics publish. It is in the unlikely branches that the picture starts to look strange. The branch in which the radioactive nucleus did not decay this hour, even though decay was overwhelmingly likely. The branch in which the cancer cell did not divide. The branch in which the plane did not lose pressure at altitude. The framework does not say these branches are absent. It says they are present, with low amplitude, alongside the much larger branches in which the more likely things happened. The version of U on the unlikely branch is not visited by special providence. The wave function does not single out anyone. It simply contains every outcome, weighted by amplitude, with no preference between them. The thought experiment with the unsettling name was first proposed in print, as far as anyone has been able to trace, by the philosopher Ewan Squires in his 1986 book, The Mystery of the Quantum World. It was independently proposed by the roboticist Hans Moravec in his 1987 book, Mine Children, and again by the mathematician Bruno Marchal in 1988. The version that became famous was formalized by Max Tegmark in a paper he circulated in 1997 and developed further in 1998. The thought experiment is known as quantum suicide. The associated claim it is supposed to demonstrate is known as quantum immortality. The setup is, by the standards of philosophy of physics, simple. Imagine a device that every second measures a quantum event with two equally likely outcomes. If the outcome is one of them, nothing happens. If the outcome is the other, the device terminates the life of an experimenter standing in front of it. In a collapse interpretation, the device works exactly as your intuition would predict. After the first second, the experimenter has a 50% chance of having died. After the second, a 75% chance. After 10 seconds, the experimenter is overwhelmingly likely to be dead. In an Everett interpretation, every measurement branches the wave function. After the first second, there is a branch in which the experimenter is dead and a branch in which the experimenter survived. After the second second, the surviving branch splits again, and so on. After 10 seconds, there is one branch among many in which the experimenter has survived 10 consecutive measurements. After 1,000 seconds, there is somewhere in the wave function a branch with vanishingly small amplitude in which the experimenter is still alive. The unsettling part of the thought experiment, the part that has fascinated philosophers of physics for nearly 40 years, is the claim about subjective experience. From the experimenter's point of view, the experimenter never experiences dying. In every branch where the device fires, the experimenter's stream of consciousness ends. In the branch where the device does not fire, the experimenter continues to be conscious. Subjectively, then, the experimenter only ever finds herself in the branches where she survived. From inside her own experience, she always continues. The branches in which she died are invisible to her because she is not there to experience them. This is the claim called quantum immortality. If MWI is correct, the argument goes, then from your own perspective, you should expect to survive every brush with death indefinitely. Not because the universe protects you, because the only branches in which your experience continues are the ones in which you happen to survive. Tegmark, when he published this in the late 1990s, noted that he might consider trying the experiment himself, but only when he was old and crazy, because in most of the branches, he would simply be dead and his family would have to bury him. There is reason to think Hugh Everett himself believed something like this. The biographical sources, including Peter Burns' 2010 biography of Everett, report that Everett took quantum immortality seriously and applied it to ordinary life. He believed, in some sense, that he would always experience himself surviving. He lived as if no version of him could die. The cost of that conviction on the people who lived with him would not become fully visible until decades after his own death. The universal wave function does not care whether any particular branch contains a conscious observer. It just evolves. The thought experiment is, as a thought experiment, contested. Most working physicists who defend MWI reject the strong form of quantum immortality. The objections are several. The probability weighting that Wallace and Saunders defended applies to the experimenter's own bets. If you weight branches by amplitude squared, you should expect your stream of consciousness to terminate, on average, with the same frequency the Bohr rule predicts. The thought experiment in this reading does not give the experimenter immortality. It gives the experimenter a vanishingly small subjective probability of surviving, with the corresponding subjective probability of being one of the many branches in which she died. The deeper objection is moral, and it is the objection the thought experiment is most often presented to highlight. Quantum immortality, even if you accept it in its strong form, only works for the survivor. From the perspective of the experimenter, she always finds herself alive. From the perspective of everyone who knew her, in almost every branch, she died on the first second of the experiment. The branches in which she survived are, statistically, far outnumbered by the branches in which she did not. Her family, her colleagues, her friends, in the overwhelming majority of branches, bury her. The experimenter does not experience that. They do. This is the asymmetry that makes the thought experiment cruel rather than consoling. Even if the survivor's subjective experience continues forever, the people they leave behind are real, on the branches where they are left behind. The grief in those branches is real. The funeral in those branches is real. The wave function does not redistribute pain. It simply contains all the outcomes. What MWI does to the experience of being a self, then, is genuinely strange, and even its defenders disagree about how strange. The framework leaves three questions on the table that we have touched but not resolved. Why do we observe the probabilities we observe, given that all outcomes occur? What does it mean to be any particular branch of you, given that all branches are equally part of the wave function? And whether quantum immortality is a coherent claim or a misleading thought experiment that the math does not actually license. There is one more piece to this story that almost no popular telling includes. It is about Hugh Everett himself, about who paid for the math, about what it cost him personally to spend a lifetime believing that no version of him could really die, while the people around him discovered, slowly, that the man they were trying to love was not entirely present on the branch they happened to share with him. Most coverage of this stops here. There is a deeper layer. It has to do with Hugh Everett himself, with who paid for the math in years of his life and years of the lives of the people who loved him. Everett, after the Copenhagen disaster in 1959, stopped publishing on quantum mechanics and stayed at the Pentagon. He worked at the Weapon Systems Evaluation Group from 1956 to 1964. He was promoted in 1957 to director of the WSEG's Department of Physical and Mathematical Sciences. He led classified studies on every major question the United States military asked about nuclear war. He helped design the single integrated operational plan, the master plan for fighting a global nuclear war in its earliest forms. He participated in deliberations that shaped how the Eisenhower and Kennedy administrations thought about the survivability of nuclear conflict. In 1959, with the physicist George Pugh, he co-authored a classified study titled The Distribution and Effects of Fallout in Large Nuclear Weapon Campaigns. The study calculated with quantitative rigor what would happen to American and Soviet civilian populations under different scenarios of strategic nuclear exchange. The numbers were not abstract. Tens of millions of deaths in the United States, many more in the Soviet Union, radioactive contamination of the food supply lasting decades. The study was a major piece of the intellectual case made within the defense establishment in the late 1950s and early 1960s that a winnable nuclear war was a fantasy. The case won. Mutually assured destruction became official American doctrine. Eisenhower and Kennedy declined the early advice of generals who had argued for preemptive strikes. The work of analysts like Everett and Pugh, quietly and with no public credit, helped persuade two administrations that there was no version of nuclear war the United States could plausibly fight to a positive outcome. The historical irony is hard to avoid. The man who had proposed, in his thesis, that every quantum outcome occurs in some branch of the wave function, that there is no single timeline, that all possibilities are equally real, spent the rest of his working life doing the precise quantitative analysis that helped ensure that the worst possibility, the one almost everyone living through the late 1950s was afraid of, did not occur on the branch we are living in. In August of 1964, Everett left the WSEG and co-founded Lambda Corporation with several colleagues. Lambda took the mathematical methods developed for classified military analysis and tried to apply them to civilian problems. The company was absorbed eventually into General Research Corporation. In 1973, with a former Lambda colleague named Donald Riesler, Everett founded DBS Corporation in Virginia. DBS did government contracting work, primarily analyzing the effects of affirmative action programs for federal departments. Everett worked at DBS for the rest of his life. He made enough money to live well. He drank heavily. He chain-smoked. He kept his physics work in a desk drawer. While at Lambda and DBS, Everett also produced original work in operations research that had nothing to do with quantum mechanics. He developed what is now called the attribute value method for analyzing complex preference structures. He extended the generalized Lagrange multiplier method into a practical tool for optimization problems that had previously been intractable. His operations research papers are still cited in the literature. Several of his Lambda colleagues, applying his methods commercially, became millionaires. Everett, who spent more than he earned, did not. The personal cost is the part of the story that the popular telling of MWI almost never includes, and it is the part that makes the framework feel different once you know it. Everett was, by every account from the people who lived with him, distant. His son Mark, the musician, has described his father in interviews as a lump of furniture sitting at the dining room table, cigarette in hand, glass of liquor next to him, rarely speaking. The household, in Mark's recollection, was emotionally remote. His father lived inside his own head, in a way that his children craved access to and were never given. There are biographical accounts from Peter Burns' 2010 biography of Everett and from Mark Everett's own writing and interviews that suggest Everett took his framework personally. He appears to have believed, in some form, in quantum immortality. He lived as if no version of him could die in a way that mattered. He paid no attention to his health. He ate whatever he liked, smoked 3 packs of cigarettes a day, drank to excess, and refused to exercise. By the late 1970s, he was overweight and his physical condition was deteriorating. His wife, Nancy, who had married him in 1956, increasingly lived a separate life. The marriage held, but barely. In June of 1982, Everett's daughter Elizabeth, then in her mid-20s, made her first serious suicide attempt. She took an overdose of pills. Mark, her younger brother, who was 19 at the time, found her unconscious on the bathroom floor. He got her to the hospital in time. She survived. When Mark came back to the house later that night, he found his father reading the newspaper in the living room. According to Mark's later recollection, Hugh looked up from the paper and said mildly, "I didn't know she was that sad." Elizabeth survived the 1982 attempt and was hospitalized for several weeks. She had been diagnosed, by that point, with severe depression and bipolar disorder. She would spend much of the next 14 years in and out of psychiatric care. The combination of her father's death 1 month after her attempt and the absence of any meaningful conversation with him in the time he had left would shape the rest of her life. Mark, who continued to live with the family through his teenage years, watched it happen. 1 month after Elizabeth's attempt, on the night of July 18th into July 19th, 1982, Hugh Everett died at home in McLean, Virginia, of a heart attack. He was 51. Mark, who was 19, found his father's body in the morning. Hugh had made one strange final request to Nancy. He'd asked that after his cremation, his ashes be thrown out with the household garbage. Nancy honored the request. Whatever Hugh believed about the wave function, he believed it consistently. He did not want a grave. He did not want a marker. He did not want, in the branch where his consciousness had ended, anything that would treat his death as a more important event than it was. The other branches, where he was still alive, would not be affected by what was done with the body on this one. Elizabeth never recovered. She struggled with mental illness and addiction for the next 14 years. In 1996, at 39, she ended her life with an overdose of sleeping pills. she left a note in her purse. The note asked, in language that everyone who knew the family understood immediately, that she be cremated and that her ashes be thrown out with the garbage. She wrote in the note that she wanted to end up in the correct parallel universe to meet up with Daddy. Mark Oliver Everett, the surviving child, became a musician. He had founded the rock band Eels in the mid-1990s. Their debut album, Beautiful Freak, appeared 2 months before Elizabeth's death. The band has, in the years since, produced more than a dozen albums. In a 2005 song titled Things the Grandchildren Should Know, Mark sang lyrics about his father that he had never been able to say out loud during his father's lifetime. The song is, among other things, an admission that the son had never understood the man. In 2007, Nova aired a documentary on Hugh Everett, made in collaboration with the BBC, called Parallel Worlds, Parallel Lives. Mark Everett, then in his mid-40s, travelled to the places his father had worked. Princeton, Copenhagen, the Pentagon. He sat with physicists who had taken his father's work seriously after the long gap of indifference. He read his father's papers, which had been recovered in the early 1990s from boxes in his mother's basement. He was, for the first time in his life, able to begin to understand what his father had been doing. In the documentary, Mark sat across the table from Max Tegmark at MIT, who explained the Level 3 multiverse to him. He stood in the Princeton archives reading his father's handwritten thesis drafts. He visited the Pentagon office where his father had worked. He looked at his father's classified analytical reports, declassified decades after their original use. The recurring image across the documentary was of a man trying to enter a relationship with a father who had died 25 years earlier. The relationship would have to be one-directional. Mark would do all the work. There is one scene in the documentary that is still difficult to watch. Mark visits a physicist named Lev Vaidman at Tel Aviv University, one of the contemporary defenders of MWI. Vaidman tells Mark, with the friendly bluntness of an academic, that he believes Hugh and Elizabeth are both still alive in many branches of the wave function, and that the wedding photograph of Hugh and Nancy hanging in Mark's apartment is, in some branches, a photograph of a marriage that is still going. Mark, on camera, does not know what to say. The framework his father invented is offering him a form of consolation he is not sure he wants, and that he is not sure he is allowed to accept. In 2008, Mark published a memoir of the same title as the song. The book covered his entire life, including his father's distance, his mother's slow withdrawal, Elizabeth's death, and his own struggle to understand the man he had grown up with. The memoir included details Mark had not been able to put into songs. The cigarette burns on the dining room table where his father sat. The years his father spent in a chair in the living room, drinking and reading and not speaking. The afternoon Mark found his father's body, and the rest of the day after. The memoir, like the song, was an attempt to begin a relationship with a father who had been gone in one sense for the entire time Mark had known him, and in the other sense for 26 years by the time the book was published. The papers Mark recovered from the basement after his mother's death in 1998 were unsorted, undated, and in many cases handwritten in the margins of other documents. Mark stored them. He did not know what to do with them. In the early 2000s, a journalist named Peter Byrne, who had been working on a profile of Everett for Scientific American, asked Mark whether the family had any archival material. Mark turned over the boxes from the basement Byrne spent the next several years working through them with technical advice from the Oxford program and the Los Alamos decoherence community. The boxes contain the original long manuscript of Everett's thesis, the correspondence with Wheeler, the correspondence with DeWitt, the unpublished philosophical essays Everett had written in the early 1960s, and an internal log of the Pentagon work as far as classification rules allowed. Byrne's biography, published by Oxford University Press in 2010, was the first full account of Everett's life and work to draw on all of this material. Byrne titled the book The Many Worlds of Hugh Everett III, Multiple Universes, Mutual Assured Destruction, and the Meltdown of a Nuclear Family. The subtitle is exact. It is, by the time you finish reading, not a metaphor. The slow vindication of Everett's framework began in earnest the year before he died. In 1977, John Wheeler invited Everett to give a talk at the University of Texas at Austin. Wheeler, by then, had quietly distanced himself from his students' framework. He had written in the early 1970s that he found the framework's metaphysical extravagance, the proliferation of unobservable branches, philosophically uncomfortable in a way he had not initially grasped. He did not retract his earlier support of Everett. He simply stopped advancing the framework. Everett, who had stopped advancing it himself 15 years earlier, did not seem to mind. The two men remained on cordial terms until Everett's death 5 years later. Wheeler outlived his student by 26 years, dying in 2008 at the age of 96. His obituaries credited him with naming the black hole, the wormhole, and quantum foam. They mentioned his role as Everett's thesis advisor in passing, if at all. In the late 1970s and early 1980s, Wheeler had become preoccupied with a different question, which he called it from bit. He came to believe that the deepest layer of physical reality was information rather than matter or wave function. He spent the last 20 years of his career working on this idea. The relationship between it from bit and Everett's framework was, in Wheeler's writings, never quite resolved. Wheeler treated Everett's thesis with affection but at arm's length. He had championed it as a young advisor. He had distanced himself from it as an established figure. He had returned to it in private conversation late in life. He never wrote in print that Everett had been right. He also never wrote that Everett had been wrong. Among the people in the audience at the Austin talk was a young British graduate student named David Deutsch, then in his mid-20s, who would go on to become one of the founders of quantum computation and the most prominent academic defender of MWI of his generation. Deutsch later credited the 1977 Austin meeting with Everett as the turning point in his own thinking. The Oxford program emerged in the decade and a half that followed. Simon Saunders, David Wallace, Hilary Greaves. The decoherence work matured at Los Alamos and Heidelberg. Sean Carroll at Caltech took up the cause for general readers in 2019 with Something Deeply Hidden. Carroll also, in the same period, launched a long-form interview podcast called Mindscape, which has run hundreds of episodes featuring physicists, philosophers, and scientists working at the foundations of the field. The podcast became, for many general listeners in the late 2010s and early 2020s, the primary entry point into MWI. Episodes with David Wallace, with Sabine Hossenfelder, with Anton Zeilinger, with Adam Becker made the case for and against many worlds in accessible language. The contemporary picture of MWI, in popular awareness, is to a large extent the picture Carroll's podcast and books have built. Brian Greene, the Columbia University string theorist who had made his name with his 1999 book, The Elegant Universe, devoted a chapter of his 2011 book, the hidden reality to MWI. Green's treatment was, in characteristic Green fashion, accessible and even-handed. He argued that the framework is intellectually serious, that the parsimony argument has real force, that the implications for personal identity are strange, but not on those grounds wrong. Green did not advocate MWI in the strong way Carroll has, but he gave it the most sympathetic mainstream treatment a non-defender had ever produced. By the early 2010s, the framework had moved into the kind of popular science discourse where it could be discussed by ordinary readers without specialized training. David Wallace, working at Oxford through the 2000s, published in 2012 a book called The Emergent Multiverse with Oxford University Press. The book ran more than 500 pages. It was an attempt to make the case for MWI at full philosophical rigor, addressing every major objection that had been raised against the framework over 50 years of debate. Wallace handled the preferred basis problem through decoherence, the probability problem he addressed through the decision-theoretic argument he had developed with David Deutsch, personal identity he treated through a careful generalization of Parfit's framework, and he extended the treatment to questions about relativistic quantum field theory that earlier defenders had largely skipped. The book did not convince the critics. It did, however, set the standard for how MWI would be defended in serious academic philosophy of physics from that point forward. Anyone arguing against MWI after 2012 would have to engage with Wallace's specific arguments. Anyone arguing for MWI would cite the book. It is, by general agreement among working philosophers of physics, the most rigorous defense of the many worlds interpretation that has ever been written. What Wallace's book did, beyond making the academic case, was establish that MWI was no longer a fringe position requiring eccentric defenders. The framework had a full philosophical infrastructure. Decoherence supplied the mechanism. The Born rule had a derivation that could be defended in a journal. The treatment of personal identity now connected with mainstream analytic philosophy. The Copenhagen interpretation still had the larger share of working physicists, but Copenhagen did not have a comparable infrastructure. It still depended at its core on the collapse postulate that Bohr had drawn around the line he could not specify. In 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for their experimental work on Bell's theorem and quantum entanglement. The press coverage of the prize often suggested that the experiments had proven the multiverse. They had not. The Bell experiments rule out local hidden variables theories. They do not distinguish between Copenhagen and many worlds, because the two frameworks make identical predictions for every Bell test ever performed. Whether the framework Everett proposed is the correct reading of quantum mechanics, or whether Copenhagen is, or whether some interpretation nobody has yet articulated will eventually replace both, remains exactly as open as it was in 1957. The Bell experiments narrowed the field of acceptable interpretations. They did not, by themselves, pick a winner. What the framework offers, if you accept it, is the picture the title of this video describes. Infinite versions of you must exist, in the precise sense Everett's relative state formulation gave the claim, on the branches of a wave function that does not collapse. The framework does not say these versions are similes. It says they are descriptions of what the equations of quantum mechanics, taken literally, contain. The honest version of the claim is sharper than the popular version. It is not that the multiverse is settled physics. It is not that all physicists secretly believe it. It is that the most internally consistent reading of quantum mechanics, the one with the fewest extra postulates, the one that takes the actual equations at face value, rather than adding a collapse rule with no mechanism, implies that infinite versions of you must exist. Whether to take that reading literally is a choice, and physicists have made the choice in roughly the proportions the polls show. The choice is not, in the strict sense, decidable by experiment. It may never be. What is at stake in the choice is the question of which intellectual cost you are willing to pay. The Copenhagen cost is that an extra postulate is glued onto the formalism with no mechanism, no equation, no specified trigger. The Everett cost is that you accept that everything the equation allows actually happens in a wave function whose branches you cannot access from inside any one of them. The question is no longer whether other versions of you exist. The question is which version of physics you find more honest, and whether you, sitting where you are sitting now, can read the equations as Everett did and accept what they say. These calculations reveal that being a single person is fundamentally different from what we ordinarily think being a single person is. You started this evening with what felt like the most ordinary fact about yourself. One body in the room, one breath, one version of this moment that you are the inside of. By Everett's framework, that feeling is not a description of how things are. That feeling is a description of how things look from inside any one branch. The feeling of being singular is what every branch feels like. The version of you who chose differently, the version of you who said the thing you held back, the version of you who never opened this video, each of them, inside their own branch, has exactly the same feeling, the same body in their own room, the same breath, the same version of their own moment that they are the inside of. There is no contradiction between the math of infinite branches and the experience of one. They are the same fact, viewed from two different perspectives. The math sees the wave function from outside, in all its branches at once, with no preferred branch. The experience sees one branch from inside, with the others invisible. Both perspectives are true. Neither is more real than the other. The framework Everett spent his life building, and that DeWitt named and Zurek made mechanical, and Carroll defends, and the polls show 15% of working physicists accept, is simply the version of physics that lets both perspectives sit in the same equations without contradiction. You came into this story understanding quantum mechanics in the version a textbook would give you, the version Bohr's group taught for 90 years, the version with two processes glued together, smooth evolution between measurements, instantaneous collapse during measurement, no equation for the collapse, no mechanism, no agreed timescale. You leave understanding it in the version Everett actually wrote down, in the long manuscript that Wheeler had him cut, that Princeton finally published in 1973 under the title The Theory of the Universal Wave Function, the version with one process, the version with no collapse, the version with branches that come for free out of the equation without being added on top of it. You came in carrying the singular present as the most obvious fact in the world. You leave understanding that the singular present is the inside of one branch of an object that has no edge. What changes if MWI is correct? Less than you might fear. The cup is still in your hand. The breath you just took is still real. The person you love is still here, on this branch, where you can reach them. The grief you carry is still grief. The choices you made on this branch still have consequences on this branch. The framework does not redistribute pain or joy across branches you cannot access. It does not make the version of you who chose differently your responsibility. It does not make the version of you on the unlikely branch your reward. Inside any branch, the experience of life is exactly what it has always been. The wave function does not need you to do anything different. It does not need you to feel anything different. You do not have to mourn the version of you who never came back from that summer. You do not have to congratulate the version of you who took the job you turned down. The other versions are not asking for your attention. They are not interested in your gratitude. They are, in the strict structural sense the framework allows, on their own. The framework gives you no responsibility for them. They are not waiting for you to acknowledge them. They are running their own lives, on their own branches, with no awareness of the branch you happen to be on. What changes is the answer to a single question. The question is, are you the only one? And the answer the framework gives, taking the equations at face value, is no. You are this one. You are not the only one. The universal wave function does not stop branching. It does not know how. It has been branching for 13.8 billion years, ever since the moment the early universe was hot enough and dense enough for quantum events to begin generating distinguishable outcomes. It will keep branching long after you are no longer in any of the branches that contain you. In all the branches where humans went extinct 10,000 years ago, in all the branches where the asteroid that killed the dinosaurs missed, and the dinosaurs are still here. In all the branches where this conversation never happened. In all the branches where it did. What I find when I sit with this picture long enough is that it does not feel like a multiplication of selves. It feels, against all expectation, like the opposite. It feels like the singular present, the version of this moment you are the inside of, gets quieter, smaller, more precise. There is one of it here where you are. The wave function is also doing many other things. In many other places it has no word for. But here, on this branch, in this room, there is one breath at a time. There is one heartbeat. There is one of whatever thought you are about to have next. There is something I want to say about the people we have lost. The framework does not bring them back. The version of them you knew is the version on the branch where their life ended. The wave function may, in its other branches, contain versions of them where the diagnosis went differently, where the car missed, where the disease did not advance. Those branches are not consoling. They are not where you are. The grief you carry for the version you knew is the grief that belongs to this branch, and it is not made lighter by the existence of others. What the framework allows you to do, if you want, is to hold open the structural possibility that they are not entirely absent from the wave function. They are absent from this branch. They are absent from the version of the world you and they shared. But they are, in the structural sense, somewhere in the wave function, in some shape, on some branch. The framework does not erase you. It locates you. You are not all the versions. You are this version, the one with this breath, this body, this room, this hour of the night. The other versions are real, in the framework sense. They are not here. You can let them be wherever they are. There is one body in this room, one breath, one version of this moment that you are the inside of. There are others. They are inside the same wave function. They cannot reach you. You cannot reach them. They are not in any way that matters to the breath you are taking now, on this branch. The wave function carries them all forward, smoothly, in the dark. You are on the branch where you are. That is where the wave function is being you. That is where you get to be.